Hello everyone, and thanks for watching Edupedia World Video. In this video, we'll be studying about the Coulomb's law of magnetic field, which is called Biot-Savart law. So, the standard generic form of Biot-Savart law is, remember, magnetic fields are created due to moving charges, which are also called currents, just like electric fields are created due to stationary charges. So, if this is a randomly shaped wire carrying a current I, in that case, the magnetic field due to this small part, say, of length dl. So the magnitude of this length is dl and the direction is the same as that of I, right? The magnetic field due to this small element of length dl at a distance r away, where r is this vector pointing towards the point P, the magnetic field due to this element dB is given by mu naught by 4 pi I times dl cross r by r cube, right? So this is the most important formula of magnetic field, and just like in Coulomb's law everything was derived from the formula for electric field and the force on a charge, I apologize, this should have been a rectangle. This is the formula for magnetic field, and this is called Biot-Savart law. Now, the first question we need to address is, why is it that in Coulomb's law, we didn't talk about a differential electric field, but a generic electric field? Well, that's because we assumed it to be a point charge of a finite magnitude q. So what will happen is, if there was a small charge dq, that would have a certain electric field at this point. If we had added more charge, that would have some more electric field at this point. But as we keep on adding charges, they will all have the same magnitude and direction of electric field in this direction. So all of them will add up to give me the net electric field due to Q in this direction. That primarily happens because Q is a point charge. We could add another charge Q in this location itself, and it would give its own electric field, and so the net electric field will be double the original value by superposition principle. In Biot-Savart law also superposition principle is valid, but a current carrying wire is by definition an extended object. So the magnetic field at this point due to this wire is different from the magnetic field at this point due to this wire, and is different from the magnetic field at this point due to this section of the wire. So to calculate the magnetic field due to an extended wire, we have no choice but to calculate individual magnetic fields and integrate it. We could have done it here as well, but all that would have happened was that we would have gotten an integral of dq, because everything else would have been the same, right? Nothing else, the electric field or anything, depends on what charge is here. So the integral of dq would have become q. But here, as dl changes, r also changes. This point has a different r vector. So that's the reason we have an extended magnetic field and this formula, because this is by definition an extended object. The other thing, mu naught is analogous to the permittivity of free space, which was epsilon naught. It is called permeability of free space, and its value is equal to 4 pi into 10 to the power minus 7. I don't remember the units, but it's standard SI units. Whenever I mention a value, it will always be in standard SI units. Now, one of the most interesting things I find in this law is that mu naught is exactly this. Now, epsilon naught has been measured experimentally, and it has a value up to a certain number of significant digits and so on. But this is the value of mu naught to an infinite number of significant digits, and that is because mu naught has been chosen to be this value, right? It might not make sense to you, but it will if you really think about it. If we have already decided the units of force, then we get to decide units of epsilon naught and so on. But once previous units are ambiguous, we need to decide one unit, it may be any unit, and then move on from there. So one of the freedoms we have in electromagnetism is to choose our constant of mu naught depending on how strong we want a magnetic field to be. We could take mu naught to be 8 pi into 10 to the power minus 7, and then every magnetic field in the world would be double its original value. But as long as we take care of every other correction, our final answers will be the same. right? So mu naught has been chosen to be 4 pi into 10 to the power minus 7, and that's quite fortunate because mu naught by 4 pi is 10 to the power minus 7. It gives us nice values. Why then do I not just write it as 10 to the power minus 7 and cancel these in the first place, you may ask? Because eventually we will have different materials which will not exactly behave like free space. They will have some mu value, and so this formula is quite acceptable. Right, just like epsilon, from epsilon naught in free space we could go to epsilon within a dielectric. From mu naught in free space we could go to mu within a magnetic material, like, right, like iron or something. So now let's just start by taking some standard current distributions and calculating the magnetic field due to them. Keep in mind that right now what we'll do is, for example in this case, we'll try to calculate the magnetic field due to a straight current carrying wire. This is analogous to the electric field due to a single point charge, because the fundamental particle in electricity was a single point charge, stationary. A fundamental particle in magnetostatics is a steady current, infinitely long. Right, this is the most basic thing you can have. Now one thing, we'll be focusing on calculating the magnetic field, let's say at a distance r. But we won't be focused on what will happen to another particle over here. For example, once we would have calculated electric field here, the force on any charged particle would have been that particle times the electric field. But the force due to a magnetic field or a current is not in the direction of the current. It's not even directly proportional to the current if you take the direction into account as well. It's somewhat complicated. So that will be for the next video. Right now we are calculating magnetic field due to a current, and in the next video we'll see what that magnetic field does to another smaller current that might be placed here. Right. So what we'll take is, initially we'll take these two angles, the angles subtended by the endpoints, to be theta 1 and theta 2, and we'll calculate in terms of that. And finally, if we want to calculate the magnetic field due to an infinitely long wire, we'll put theta 1 and theta 2 both equal to 90 degrees, and that will give me an infinitely long wire. Right, so let's start with this calculation. So we'll take this as the origin. I purposefully took this not to be the midpoint so that you can see theta is not equal to theta 2. I'll take this to be the origin. At a distance x away from the origin, I'll take a small element of thickness dx. I'll calculate the magnetic field due to this element, and I'll integrate it and make theta, which is the angle subtended here, this theta, or actually to be honest there should be 2, and this is theta and this is d theta. So what I'll do is I'll calculate the magnetic field due to this element at this point. I'll integrate it to get the magnetic field due to the whole wire, and I'll make theta go from minus theta 2 to theta 1, because theta 2 is in the opposite direction. If you took theta 2 to theta 1, then you take theta 2 in the upward direction and it would have calculated the magnetic field due to this element, right? But we want the whole element, so minus theta 2 to theta 1. So theta will go from minus theta 2 to theta 1. Once you start increasing your level and start preparing for higher level entrance examinations, these small things like this minus become really important, right? So stay calm and focus on getting no errors initially, and you can reduce the time taken to solve questions later. That's what I always tell to my students, that once you know the topic and once you can solve questions, successfully reducing the time taken to solve each question will come very easily. It will come in a matter of 2 to 3 weeks once you know how to solve the problem. But if you're focusing on two things together, solving the problem and not making errors, plus doing it within a finite amount of time, it adds an extra pressure, and you can just leave the second part for later, right? So the first thing we need to do is find the relationship between dx and d theta. Now I'm going to show you two methods to do that, just because the first method will be a purely algebraic method and it might seem to you to be very abstract and not very rigorous. So the first method would simply be, what is x? X is equal to r times something. What is that? So that is this by this is tan theta, right? So we'll get x by r is tan theta. So x is equal to r times tan theta. From that I'll get dx is equal to r times, r is a constant, derivative of tan theta is sec square theta d theta. So this is the equation I was looking for, because initially my magnetic field it will be in terms of dl, that is dx, but I'll need it in terms of d theta. Now this equation, if it seems slightly abstract to you, let me just show it in the figure and show that it indeed is like that. The problem is when you do it geometrically, there are chances of making errors. That's why I choose the algebraic method first. But let me just enlarge this particular portion. So it looks something like this. This is dx. These 2 points are very far apart. This is a very small angle, d theta. This is r. This theta. This theta should be much greater than d theta. So I've actually made a mistake in making the figure. But this part is important. I've enlarged this, right? So now this is r. So what is this? This particular quantity will be r tan theta. Right? Now you draw a perpendicular from this point like this. So if this is r tan theta, we can take this to be r tan theta as well. Right? Now if this is d theta, what is this going to be? This is d theta, this is 90 degrees. So this is 90 minus d theta, or this will be d theta. Right? Sorry, I made a mistake. This is r tan theta. So this is not r tan. This is r tan theta. What is this? This into cos theta will be r. So this is r sec theta. Similarly, considering an isosceles triangle, this will be r sec theta. Right? Now, if this is r sec theta, what is this? This will be this times d theta, right? That's the formula you have. dl is equal to r d theta. So this will be r sec theta d theta, right? Now this into cos theta is equal to this thing. So this thing is equal to this by cos theta. So dx cos d theta will be this. So dx will be r sec square theta d theta, right? So you can calculate it in both methods. In fact, if you really think about it, what we've done is we've proved that the derivative of tan theta is sec square theta geometrically. And in fact, when Newton first started to prove out that example, the derivative of x square is 2x, he didn't do it algebraically, he did it geometrically, right? It was much harder, but that's how people understood it at that time. So this is direct by derivation, but I'll repeat it again. Take this triangle. This is r. The hypotenuse times cos theta is equal to r. So the hypotenuse is equal to r by cos theta, or r sec theta. Then this is equal to r sec theta d theta. And this into cos theta is equal to that. So this is equal to r sec square theta d theta. Right? So I'm going to rub this now, because this is not important. But this is important, because as you increase the level of questions you are doing, and as you try to calculate electric magnetic fields or something else for more and more complex structures, you'll keep encountering things like these where you'll have to calculate one differential quantity in terms of another. Let's move forward now. The magnetic field at this point will be mu naught by 4 pi times I times dl, which is dx cross r. Right, now what is r? R is this distance. So this is actually r sec theta now, by r cube, which is r cube sec cube theta. Right. But what is the direction now? We haven't focused on the direction yet. So it is dl cross r. This is the direction of dl, right? And this is the direction of r. So what is dl cross r going to be? It's going to be inside the page. By the way, this is my convention for inside the page. Not my convention, everybody uses it. And this is for outside the page, coming out of the page. So if you put your right hand towards this vector, and you curl your right hand towards this vector, then your thumb should point inside the page. So the direction of electric field is inside the page, right? Actually, that's quite fortunate for us, because when it's inside the page, we don't have to take any component, right? We can just integrate it, because all the electric fields point inside the page. One thing is still missing, however. This is A into B, but A cross B is actually mod A mod B sine theta. So we have to add a factor of the angle between dx and r. What is the angle? If this is theta, this is 90 minus theta. So what is this angle? This angle is 90 plus theta. Right? So the angle between DLR is 90 plus theta, and sine of 90 plus theta is cos theta. Right? So we'll have a cos theta here. Now dx, we'll just write it as r sec square theta d theta, and we see that sec square theta and sec theta cancels with sec cube theta, and these two cancel with 2r's, and what we get is, and there's a d theta obviously, so dB is equal to mu naught I by 4 pi r integral of cos theta d theta. So now that's it, integrate, and theta will go from minus theta 2 to theta 1. When it comes to cos theta, it doesn't really matter. So, but if the integral of cos theta will be sin theta, so for that it will matter. So the final answer will be mu naught I by 4 pi r sin theta for theta 1 and minus theta 2. So sin theta 1 plus sin theta 2. Right? So this is the final answer. I'll repeat once again what I did. I took a small element of length dx at a distance x away from this. I calculated the relationship between dx and d theta. If you actually were well versed in mathematics and integration, what you could try to do is you could try to integrate it in terms of dx, and this, for example, if this is theta 2, this will be r tan theta 2, this will be r tan theta 1. So x would go from minus r tan theta 2 to r tan theta 1. I'm sure you'll get the same answer. Right, so I wrote it due to an element. Fortunately, the field due to all elements were pointing in the same direction inside. I wrote it due to 1 and I integrated it, and I got this answer. Now what if this were an infinite wire? Then theta 1 and theta 2 both would be 90 degrees. Sin theta 1 and sin theta 2 both would be 1. So the answer would be mu naught I by 2 pi r. Right. So these two are important formulas which you need to remember. This is for a standard straight wire subtending angles of theta 1 and theta 2, and this is for an infinitely long wire a distance r away from it. What is the direction? There's a very nice way to find the direction as well, and we see this again and again when we are using cross product, and this comes from the cyclic property of cross product, which says that A cross B dot C is equal to B dot C cross A, and so on. Right, I'm sure you know that cyclic property. So what happens is, this is the wire, this is the dx element, this is r. So one way you could find the direction is dl cross r, and that will give you inside the plane. But another interesting way of finding the direction in the case of a straight wire is, I'll try to make a hand here, though I'm not that good at drawing. Yeah, you put your thumbs in the direction of the electric current and curl your fingers around the wire, and the right hand obviously, and the direction in which your fingers curl will be the direction of magnetic field. Right, so at this point the magnetic field will be inside the plane. At this point, this is dl and this is r, so dl cross r will be coming out of the plane. If you go like 10 meters inside the plane from here, the magnetic field will be towards the left. Right, try to imagine it and do the cross product. If you go 10 meters towards yourself, that is away from the monitor towards yourself, in this point magnetic field will be towards the right. And if you look at it from the top, if this is the direction of electric current, that means electric current is coming towards you, right? That means your eyes are somewhere here and electric current is coming towards you. In that case, this will be the direction of magnetic field. And just like we have the concept of electric field lines for electric field, I won't say a lot about it, but the magnetic field lines also exist. They can never intersect, and the number of magnetic field lines per unit area represents the magnitude, and so on. Same for electric field lines. This is the direction of magnetic field lines for a current carrying conductor coming out. If this was going inside, then you put your thumb in this direction going inside, and your fingers will curl towards the right in the clockwise direction. So that will be the direction of magnetic field. Right. So we've tackled our first obstacle, trying to find out the magnetic field due to an infinitely long stationary wire. Next step, magnetic field due to a circular current carrying loop at its center. Next we'll go to a point at its axis. Right now we'll do at its center. So this is a current carrying loop of current I, radius is r. We need the magnetic field at its center. So we'll take any point dl, right? This is r and this is dl. So the magnetic field will be mu naught by 4 pi I times dl times r by r cube. What is the angle between dl and r? That is 90 degrees, right? Because the tangent is always perpendicular to the radius. So sine theta is 1. And what is the direction of the magnetic field? This is dl and this is r. So obviously direction of magnetic field will be going inside the plane, right? So going inside the plane, we can integrate these. The only variable is dl. The integral of dl will be the total length, that will be 2 pi r, right? So 2 pi r. So 2 pi cancels with this, we get 2. R and r cancel with this, remains r. And what we get is the magnetic field is equal to mu naught I by 2r. This is the magnetic field due to a current carrying loop of radius r at its center. Again, you can find the magnetic field in two ways. You can either do dl cross r and find that it's inside the plane, or you can curl your fingers around the current, right hand obviously, and your thumb will point inside the plane with the direction of magnetic field. So we see two separate methods again of finding the direction. Pure dl cross r, or curl your fingers around I and your thumb will point towards this, or curl your fingers, do the same thing we did previously. This is your thumb and these are your fingers. Curl them with your right hand around I and you will see that at this point it goes inside the plane, and at outer points it comes outside the plane. At any point where you have a wire going like this, the electric field lines will go like this, such that if you put your thumb towards the wire, then your fingers will curl towards the direction of electric field. Always remember right hand. Right. Now let's look at the third and final case, which will be a superset of this original case. We have a current carrying loop, radius r. Let's say the radius is a for consistency, and the distance will be r. We want, and this, now it depends on whether it's going clockwise or anti-clockwise. Right now we've taken it such that if our eye is at this place, we'll see it going clockwise. That means this point is near to us and this point is far. I'm not very good at drawing two-dimensional images, but you can see the point. It is going nearer to you, nearer to the viewer. It is going up. Away from the viewer, it is going down. This is perpendicular, right? If you're looking at it from here, then you'll see it going in the clockwise direction. We need the magnetic field at a distance r, right? So let's get to it. We'll take a small element anywhere, dl. The magnetic field due to this element will be mu naught by 4 pi I times dl cross r by r cube. Right. Now what will r be in this case? First of all, r is not this distance. R is the distance between, this is dl, sorry, between this element and this, right? So this is r, this is a, this is 90 degrees. So this distance will be root of r squared plus a squared, right? So here we have r squared plus a squared to the power 3 by 2, and here we have root of r squared plus a squared. Then we have dl, that is this. Then we have to find out the angle between these two, right? What is the angle here? This is dl, this is r. Actually, let me draw the figure properly because that will be important in this. So this radius is a, this distance is r. Right. Now we take any point dl, right? So the magnetic field dB will be, it's like I said, nearer to you it's going up, away from you it's coming down. Here at the top it's going inside the plane, here at the bottom it's coming out of the plane. dB is equal to mu naught by 4 pi I times dl cross r, right? Now r is actually root of r squared plus a squared. The root of r squared plus a squared by root of r squared plus a squared whole cube. Yeah. Now the angle between dl and r is 90 degrees, because a lot of students make this mistake. They'll write the angle between dl and r in this. But this is not between DL and R, it's between this line and this line. But we want the angle between this line and this line, and they obviously are perpendicular to each other, right? So the angle between them is 90 degrees, so sine theta will be 90 degrees. Now all we need to take care of is the direction of the magnetic field. So let me do it for the topmost case, it will be slightly easier. So if I look at this element, it is going inside the plane and R is towards the right. So what will the direction be? You put your fingers inside the plane, you curl them towards R, and I'm sure you can see the direction will be something like this, where this angle is 90 degrees. Right. Similarly, if you look at the bottom, fingers pointing towards you, curl towards R, the direction will be something like this. If you look at this point, the direction will be something like this. And if you look at a diametrically opposite point, the direction will be opposite. Right. So you'll see that the vertical components of all of these will cancel out, because every diametrically opposite point will have the exact opposite vertical component, and the horizontal components will add up. So all we need to do is take the horizontal component of this and find the answer. So it will be easiest to take the topmost one. So this is A, this is R, and this is the one, right? So this angle is 90 degree. What we want is this angle. So that will be 90 degrees minus this angle, right? So we want the cos of this angle, that will be the sine of this angle. The sine of this angle will be A divided by root of R squared plus A squared, right? So into A by root of R squared plus A squared. Now if you look at this closely, everything is constant except dl. So once you integrate it to get the magnetic field, dl will be integrated to give you the whole length, that will be 2 pi A. Now all that remains is a little bit of simplification. These two cancel, 2 pi cancels with this and gives us 2, and what we get is B is equal to 2 mu naught I, sorry, this is not 2, this is 2. So B is equal to mu naught I A squared by 2 times R squared plus A squared to the power 3 by 2. Right? So hopefully now you understand how, using Biot-Savart law, we can use standard shapes and sizes and try to calculate the magnetic fields due to them. Right? Now one more thing that is left, if you take the distance to be much smaller than A, if you take R to be much greater than A, then what you get is, you can ignore A in front of R, and what you'll get is B is equal to mu naught I A square by 2 R cube, right? And if you write I pi I A squared, I should rather write it as pi A squared times I. If you write this as mu, this is, we'll see this again later on, but this is what is called the magnetic dipole moment, right? If you write it like this, then what you can get is B is equal to mu naught by 4 pi into 2 mu by d cube. Right? Now let me look at these vectors now first. Right? So mu basically points in the direction of B. That means it points towards the left. Right? Also, we know that at an axial point for an electric dipole, the electric field is equal to 1 by 4 pi epsilon naught 2p by d cube. This is the exact same equation except p is replaced by mu. Looking at that, we tend to call the mu the magnetic dipole moment. Right? So magnetic dipole moment is basically for any small loop. Right? It's generally defined for small loops. It is the current flowing through the loop I multiplied by the area of the loop, which in this case is pi A squared. And this is only valid for R much greater than A. So we see the analog of electric dipoles, which are magnetic dipoles. However, one big difference, electric dipoles are two charges, one positive, one negative, kept close to each other. Magnetic dipoles are something completely different. Magnetic dipoles are basically current carrying loops, and the direction of the dipole moment is the direction of the area. right? Assuming you curl your fingers along the right hand, along the current. So if you curl your fingers along the current, in this case, this will be the direction of magnetic dipole moment. It is also called magnetic moment sometimes, right? So this completes Biot-Savart law. In the next video, we'll see what happens when a current is placed in a magnetic field. Oh, just one small thing. Sometimes you'll have a loop and you'll wrap a wire around the loop, let's say 10 times. In that case, the dipole moment will be 10 times this, because the current goes around the same loop 10 times, right? So in the next video, we'll see what happens when you actually put a current carrying wire within a magnetic field. We'll see the analog of QF is equal to QE. Thank you.